Welcome to Lecture 5 of A Gentle Introduction to Fourier Analysis and Polytopes. My name is Sinai. I work at IME, University of Sao Paulo, and this is presented by IMPA, the Research Institute of Brazil, for Mathematics, Pure and Applied. And this is a part of the 33rd Colóquio Brasileiro de Matemática. So let's see what we have for you today. Is there a dictionary between tiling Euclidean space, d-dimensional Euclidean space, by translating some fixed convex body and some nice Fourier condition? Would we ask that question if there wasn't? Yes, we might, but it turns out indeed there is. And extremal bodies in Minkowski's theorem, so we'll recall Minkowski's theorem again and ask when does equality happen in that inequality? And that turns out to be directly related to tiling Euclidean space. And in general, some fun facts and a video as well for you today. For the geometry of numbers, it was founded again by, of course, Minkowski. And to say he was a great mathematician is always an understatement. He did tremendous amounts of things. In any case, one very nice question we can ask, simple sounding question, but with many repercussions, is again, when can we tile Euclidean space by translating some body, particular convex? And we recall first some of the definitions. What is a body? What is convex? What is symmetric? A body is defined as a closed bounded subset. In other words, compact. A set is called convex. If for any 2 points x, y in a set, the closed line segment connecting them is again in a set. And a body is called symmetric about the origin if for every x in Euclidean space, whenever x is in the body, minus x is also in the body. And so there's again, what's the natural question we start with today that motivates all of today is when do we have equality in Minkowski's theorem? Let's recall Minkowski's theorem. It said the following: let B be a d-dimensional convex body symmetric about the origin. If B does not contain any integer points in its interior, then the volume must be bounded above by 2 to the d. And 2 to the d is sharp. And so let's ask, when does equality happen? The equality occurs if and only if, of course, the volume is equal to 2 to the d by definition. But the question is, which bodies attain the equality? For which bodies B is it true that the volume is equal to 2 to the d while still maintaining these hypotheses? So we also proved last time Ziggles formula. So let's recall Ziggles formula again. Let B be a d-dimensional convex body symmetric about the origin, same hypothesis as Minkowski. And again, if the only integer point in the interior of the convex body B is the origin, then we have this kind of fantastic identity of Ziegel, Carl Ludwig Ziegel. 2 to d is the volume plus this infinite sum of the norm squared of the Fourier transform of the indicator function. Now, it's a Fourier transform of the indicator function almost of B, but to dilate, we multiply every point in B by 1/2. So that's the 1/2 B. You dilate B by a factor of a half, take the Fourier transform of that body, and evaluate it xi for all integer vectors xi except the origin. And we have an identity. So we proved this last time. And now we want to ask, when does equality happen? Well, given this identity of Ziegel, we see that the equality happens if and only if all these terms vanish. Why? Let's look at Ziggles formula again. So staring at it, we notice that all of these terms in a series are either 0 or positive. They're non-negative. And so if we want the volume of B to be equal to 2 to the d precisely, that means this whole infinite series must vanish. And since all the terms are non-negative, that means each term must vanish separately. And so we get this infinite sequence of identities that all the Fourier transforms vanish for all xi integer vectors except the 0 vector. When xi is a 0 vector, we get this, the volume of B is equal to 2 to the d because we evaluate the Fourier transform at 0. But we'll go through that evaluation computation again. And so let's record this just simple observation consequence of Ziegles formula as a lemma. Let B be a d-dimensional convex body symmetric about the origin. Suppose B does not contain any non-zero integer points in its interior, then the volume of B is 2 to the d if and only if the Fourier transform of 1/2 B at xi is 0 for all xi integer vectors except for the 0 integer vector xi. And so that's what we showed as a consequence of Ziegles formula, assuming that the volume of B is equal to 2 to the d. That assumption, by definition, means we'll use the words that B is an extremal body. And we want to relate this vanishing of the transform directly to tiling. And so the main topic of today is when can we tile by translating a convex body. So given a convex body in d-dimensional Euclidean space, we say that it tiles by translations with a discrete set of translations. Let's call it lambda for the moment. If for each x in Euclidean space, we have this identity. In other words, for each x here, notice that so each x here is covered by some n translate of B. So if this is B, we translate B by some vector n. Here's B plus n. And this n translate of B is going to contain the point x. And so for each x, there exists some translate. Here's the translate of B by n1. Here's a translate of B by some integer vector n2. And so there's always an integer vector n. In this case, a lambda vector, the n's are going to belong to just any discrete set. We're not going to necessarily assume that this lambda set is a lattice. And so we allow for non-periodic tilings of B. However, in a second, we will restrict to the case that lambda is a lattice, but in general, we want to assume lambda is not a lattice and allow for these things to happen. And so, So now what does it mean for except for x to be in a boundary of B and its translates? Let's look at a picture, and let's make this picture a little bit easy to read by deleting these drawings. And so here's a square. We're going to tile the two-dimensional plane by translates of the square. So first, we move it to the right by the vector 1, 0. So that's an integer vector. So in this case, the set of translation vectors consists of all the integer vectors in the plane. And notice that the boundary, this green segment that I drew here, means that the boundary of these two squares gets covered more than once. And so that equality that we said, it fails for the points in the boundary and the translates of the boundary. Except for that measure zero subset, except for those points in the boundary and their translates under all the integer vectors in this case, except for those, all the other points in the interior and all the translates of the interior, they do get covered exactly once. And so here's another translate, another one, and we keep translating forever all the squares until they fill up the two-dimensional plane. Back to the definition, given a convex body, we say, or in fact, any body, but we say that it tiles by translations with a discrete set if for each x we had this equality. Once you have an identity like this, an equation, it's kind of wonderful because then you can also do all sorts of things. Maybe you can take the Fourier transform of it, maybe you can do Poisson summation, maybe you can do other things, convolve or other creative things. And so now we can do something. So first we can notice we'll notice in a second that the series is in fact a periodic function of x. But let's see. So in other words, given any generic point x, just to review what we have here, any generic point x in Euclidean space, this definition of tiling by translates says that there is some translate of B, say B plus n, which contains x. That's what the identity says. Now let's restrict to the case of a lattice. Why do we differentiate between an arbitrary set of translations, capital lambda, and a lattice? Because some parts of the theory, when we go to more general theories, we want to allow for non-periodic structures to occur. But for now, let's restrict to a lattice. So if we have a lattice of translation vectors, then we have this identity where now we have n varying through a lattice, indeed a purely periodic structure. And now we observe that, as we said, this left-hand side, the series, can be written as a summation indicator function of B at x minus n, by definition of indicator functions. And so this means that this capital F of x is a periodic function. And those wonderful number theorists, Hecke's dictum always said, if you have a periodic function, expand it in the Fourier series, see what happens. Wonderful things will happen usually. And indeed, he was right. So anyway, let's just expand this capital F of x into a Fourier series. And And by the way, when the set of translation vectors is a lattice, we say that we have a periodic tiling by definition of the word periodic because of the lattice. And so, question, is it true that every tiling of a convex body using some set of translation vectors must necessarily be a periodic tiling in any dimension? And somewhat surprisingly, it was proved by Peter McMullen that it is true that even if you assume that the set can be any arbitrary discrete set of translation vectors, in fact, it must be a lattice at the end. So that's the case for our context. Tiling, convex bodies, centrally symmetric. In more general tiling situations, that's perhaps is not necessarily true. But in many theories that extend this one, in particular multi-tiling, for which we talk about in our book, nobody has ever witnessed a single situation when we don't have a lattice. It's kind of interesting. Okay, so anyway, let's go on. We proceed intuitively now. So this proof, quote proof, will be intuitive, and we'll come back to why it's intuitive later in the lecture. We recall Poisson summation. This is what Poisson summation said, that the Fourier series of the left-hand side, in fact, has this form where the Fourier coefficients are, in fact, the Fourier transforms of the indicator function of P. And in the Fourier transform here on the right-hand side, as part of Poisson summation, means over the whole space. You integrate over the whole space. And so this is one form of Poisson summation formula for lattices that we proved last time. But we also know, by definition, that the left-hand side of this Poisson summation formula is in fact equal to 1, because this is by definition of tiling. And so this is wonderful because now we can equate the Fourier series on the right to the constant 1. And so we have 1 is equal to the Fourier series, but imagine that we have a Fourier series on the left, except that it's constant, it's 1. So by uniqueness of Fourier series, we have infinitely many identities now. So by uniqueness of Fourier series, we have that 1 on the left must be equal to the constant term on the right. Well, what is the constant term on the right? We plug in c equal to 0, and we have 1 over the determinant of the lattice times the Fourier transform of B at 0. But we also know that whenever we evaluate the Fourier transform of 0, we already have done this a few times, we get the volume always, because Fourier transforms extend volumes. And so 1 is equal to the volume divided by the determinant. So that's nice. What else? Well, the Fourier series on the left is a constant equal to 1, so all the terms are 0 except for that constant. So all the terms on the right must be 0 as well. So we have this infinite sequence of identities, one for each integer, or rather lattice now vector xi, where xi varies over the dual lattice of L, except for the 0 vector. And so we've shown intuitively, at least, that we have this theorem. We'll call it a vanishing Fourier transform criterion. Given a convex body B, it tiles by translations with a lattice if and only if the following two conditions hold. I should have written convex, but in fact it works more generally here. So the Fourier transform of B vanishes for all xi in the dual lattice, and the volume of B is the determinant. And so we've just proved it, so let's conclude what we've done here and call it the vanishing Fourier transform criterion for tiling. This theorem is due to Mihalis Kolontsagas, and it's really wonderful. It's very, very useful in many contexts, and extensions of it to multi-tiling, which you can read in the book, and hopefully we'll come back to. So here we find another fascinating dictionary between a tiling property using translations only and a Fourier criterion. So it's another dictionary. And again, as we said, infinitely useful. All right, so now we combine the logic of the lemma together with the theorem. Let's review. We had this lemma from before, the first thing we did today, and now we have this vanishing criterion of Kolontsagas. Given a body K, it tiles by translations with a lattice, even only if these two conditions hold: vanishing of all of these terms and the constant term of the Poisson summation give us this, the second one. Poisson summation, of course, gave us both. Okay. Thinking about this lemma, by the way, let's return to the lemma. You might wonder, what is the half be doing there? What is the 1/2 doing? Also in Ziggles' lemma, what was the 1/2 doing there? Well, the 1/2 there is we can understand the one half a little bit better if we focus today on the extremal tilings, the extremal bodies. So again, back to our main question today, when do we have equality in Minkowski's first theorem? And by definition, when you have a convex body B that achieves the equality, in other words, the volume of B is equal to 2 to the D, that body is called extremal. And so the question, the theorem that we have for you today is very classical. Again, the theorem on extremal bodies. And again, due to Minkowski in this context, let K be any convex essentially symmetric subset of Euclidean space, in other words, symmetric about the origin. If the only integer point in the interior is the origin, then we have the equality, in other words, K is an extremal body, if and only if 1/2 K tiles Euclidean space by translations with the integer lattice. Okay, let's see some examples. So here's a two-dimensional convex body with integer lattice, and these points belong to the integer lattice. Let's see. Let's say expand it. As we expand it, we see that these expansions, they never contain an integer point by construction. And here's one with the largest possible area. So this is a maximal body, this particular square. It has area 4, which is equal to 2 to the D. So the volume of the body B is equal to 2 to the D, where D is equal to 2. So the volume is 4. And this is by definition an extremal body, the square. So we stare at it and we wonder, well, maybe is that the only possible one? Maybe there are others, parallelograms certainly, but any other kind of bodies besides parallelograms? So can we imagine more? Remember what the bees can do, right? Hexagons, perhaps. So let's think. After thinking for a moment, we might come up with the following picture. We might parameterize hexagon by saying, okay, let's place a point P here and look at these kind of images of P by adding the vector 2, 0, and then reflecting and so on. And you get a symmetric hexagon about the origin. The center here is the origin. And indeed, you can check that the volume, the area in this case of the hexagon is equal to 4. So this is also an extremal body in 2 dimensions. As P moves around, we get a continuously parameterized moduli space. It's called a space of configurations, that's all it means, of symmetric hexagons. Sometimes they'll degenerate to parallelograms. And so one very natural question is to kind of wonder, can we classify all of them? So I've prepared for you this video demonstration, a computerized demonstration of the extremal bodies in 2 dimensions. As you can see, let's follow this point here. As it's traversing this area in the top, sort of the top left of this little figure, you see the hexagons forming symmetric hexagons and also symmetric quadrilaterals, namely parallelograms. The hexagons when the hexagons become degenerate, they form parallelograms. And so let me see, I'm going to follow this point here with force. Let's see, I'll show you the equations I used. It's using Desmos, which is freely available on the web. And if I pause this for a second, this point here, as it traverses this region here, you can see that it's kind of mesmerizing, really. You can see that these hexagons they all have the same area. That's easy to check. That's always area equal to 4, guaranteed by Minkowski's extremal bodies. So they're all extremal bodies. And as this point travels along the boundary of this little triangle here, you see the degenerate cases are the parallelograms. One can ask, is this really all of them? It turns out, yes, this is all of them up to reflections. And this region is called the moduli space. It's this little triangle is a moduli space. Every point here represents one hexagon, one extremal body. And so this is very interesting and kind of fun to watch it. I can watch it all day. But in any case, we want to go on and prove something, of course. It's kind of sexy to see, almost as sexy as the Fourier transform of a polytope. So this picture was shown by the dynamic video that uh, we have all these extremal bodies. Each one has constant area 4 as the point traversed this region. And so we might ask, well, okay, is this all of them? Turns out there is, but we didn't prove it. You might also ask, why just parallelograms and hexagons? Why not perhaps octagons? And I encourage you to think about that. We didn't prove it, but indeed, it's a theorem that the only extremal bodies in 2 dimensions are in fact these parallelograms and symmetric hexagons about the origin. And they all have area 4 as they should by definition of the extremal bodies. And so for me, by the way, I like to think of why not octagons in terms of local angles. If you have a tiling, we can focus attention on the vertex and the angles simply don't add correctly. So it's fairly easy to see, but maybe you have a better way of seeing it. So I encourage you to think about it. Back to the last destination for today, namely, let's prove this theorem for extremal bodies. So again, we start with a convex body, centrally symmetric about the origin, d-dimensional space. We assume that the only integer point inside is the origin. Then the volume of the body is equal to 2 to the d. Namely, we have this extremal property in Minkowski's theorem, if and only if 1/2 b tiles Euclidean space by translations with the integer lattice. So there's the 1/2. And so this is natural, very natural to want this. And indeed, it's if and only if. And it's interesting that our proof goes via Fourier transforms, but if you look at the statement of the proof, it doesn't have any Fourier transforms. But it turns out that it's very convenient and easy to go through the Fourier transform landscape. So we'll recall again the 2 things we proved, the lemma, the easy lemma, and this very interesting vanishing criterion for tiling. And now we'd like to glue these 2 together. And let's see, so first we assume, of course, that B has this extremal volume, it's equal to 2 to the d, B is symmetric convex, and the only integer point is the origin. By our lemma, we know that we have this vanishing, it's if and only if we have this vanishing at all the integer points, non-zero integer points, and by the vanishing Fourier transform criterion applied now to, we have to be careful to k is equal to 1/2 b. Not k is equal to b, but k is equal to 1/2 b. And with the lattice being the integer lattice, we're done because why are we done? Let's go back to the criterion, the Fourier transform vanishing criterion for tiling. It says we have a tiling if and only if the Fourier transform of k vanishes at all the integer points except in a dual lattice of the L except the origin. If we restrict the lattice to be the integer lattice, the dual is itself, so everything is easy in the case of the integer lattice. And if we can check that this is true when k is 1/2 b, then we know by the criterion that 1/2 b tiles by translations, and that's what we want to prove. And so all we have to do is check the 2 conditions of the vanishing criterion. The first condition we already know, it's given by the lemma, and the second condition was the volume condition. Well, the volume is it equal to the determinant of the integer lattice? That was the second condition. The part B of that vanishing criterion theorem. Well, the volume of B, the volume of K by definition is the volume of 1/2 B, and the volume of 1/2 B is 1/2 to the d times the volume of B, and that's equal to 1 because the volume of B is equal to 2 to the d by assumption. So we had this. Let's go back to our assumption. We had this assumption here that the volume of B was equal to 2 to the d. And therefore, the volume of B divided by 2 to the d is equal to 1 by our assumption. And that's it. So it's kind of very nice. Everything fits together perfectly. And we have the proof of the theorem that we wanted to prove. And so what about higher dimensions? So let's see. So what about, let me try to erase this. What about 3 dimensions, for example? These are called Fedorov solids. They're fascinating. And Fedorov in the 1880s, I think 1885, proved kind of brute force, I believe that these are the only 5 convex objects in three-dimensional space that tile three-dimensional space by translations only. In doing so, he gave birth to kind of crystallography, the modern crystallography as we know it, the more modern crystallography at that time. And one might say, well, wait a second, I can perturb some of these a little bit, yes, but up to combinatorial equivalence, as we call it, these are the only ones. Combinatorial equivalence, I don't want to get into it very briefly. It just means that the incidence relations between all the edges, faces, and vertices, they stay the same. If you want to be precise, the face poset of the polytope is the isomorphic. In any case, up to combinatorial isomorphism, they all have kind of the same shape. These are the only 5 that are possible. Just like in 2 dimensions, the only 2 that were possible were the parallelograms and symmetric hexagons. And so, yeah, Fedorov classified these extremal bodies. In fact, I'm not sure, but he might have visualized in his mind, maybe, what we just shown the computer can do. Maybe he had this computerized or visual capability to visualize the 3-dimensional version of that. And by the way, if you have a 3-dimensional object that tiles, convex object that tiles Euclidean space by translations only, these are sometimes called Dirichlet-Voronoi polyhedra or sometimes parallelohedra. So this is the lingo that people use, parallelohedra. We'll just say parallelohedra, but in the literature, they're called Dirichlet-Voronoi polyhedra as well, just so you know if you look up the literature. And obviously, we want to classify them in all dimensions. Fedorov classified them in 3 dimensions in 1885. One of my favorites is this one. And indeed, we see from this picture, it suggests anyway that it does indeed tile by translations. As you can imagine, these are sometimes gems, literally gems, crystals. And this completes the study of translational tilings in 3 dimensions, at least. In 4 dimensions, it turns out there are 52 different combinatorial types. In 3 dimensions, there are 5. In 4 dimensions, there are 52. That search was done in a not so distant past. In 5 dimensions, there are 110,244 different combinatorial types. Obviously, we're not going to list them all here. That search was done very recently, 5 years ago in 2016 by Dutour, Garber, Sherman, and Waldman. Wonderful piece of work, and they completely classified all the 5-dimensional parallelohedra. In other words, 5-dimensional convex bodies, symmetric about the origin. They're going to tile by translations. By the way, we don't need to assume that they're symmetric about the origin. That turns out to be a consequence of yet another of Minkowski's theorems, which we'll mention in a second. We'll get back to it in a second. For now, let's look at 4 dimensions. There are 52, we said, 52 types of parallelohedra, things that tile by translations. This one is one of my favorites. It's called the 24 cell. It turns out to be something called a Voronoi cell of a D4 lattice, but anyway, it's a 24 cell. Here's one that's more common, tesseract. It's probably better known, but the 24 cell is more stable. And so if there were 4-dimensional bees, perhaps this is what they might build. Thinking fictionally for a moment, or rather 5-dimensional bees really, because we're already 4-dimensional creatures. But in any case, this one is more stable. So like the hexagons in 2 dimensions, that one is very stable. This 24 cell is as well. And it's a very curious creature, the 24 cell. It's quite interesting in many respects. It's self-dual. It has many interesting properties. Okay, back to Minkowski. So Minkowski proved if you have any body, and we don't necessarily assume it's even essentially symmetric, but if you have a convex body, let's say, and it translates, it tiles by translations with a lattice, then it must be symmetric, and all the facets must be symmetric. The facets are the faces of dimension d-1. In other words, the codimension 1 faces. So if the dimension of the object is d, the facets of the object p are the d-1 dimensional faces, the top dimensional faces, they all must be symmetric. And so this wonderful theorem of Minkowski is almost a characterization. Later on, Minkowski, Venkov, and McMullen together, there's a third condition, but it will take us too far afield at the moment to define things. So let's, also, you might wonder, suppose I have a convex body and it tiles by translations. Does it have to be a polytope? The answer is yes, it must always be a polytope. And that's a separate fact. Also not too difficult to prove these, but we won't prove everything today. So I just want to mention these because they're beautiful and true, so we might as well mention them. Okay. Remember when we said we now proceed intuitively and we showed that we have this vanishing criterion? We didn't prove it. Why not? What lacked? Why was the proof lacking in rigor? Let's talk a little bit about that. We applied the Poisson summation formula, remember, to the indicative function of a polytope. It turns out we technically can't do that because the Fourier transform is not even an L1. It's certainly not a Schwartz function, but it's also not an L1. That's, at the moment, this is a hard exercise to do without further theory. But if you look in our book, you can develop, we'll develop, as we develop further theory, as you read through the book, you'll be able to prove this later on. There is a different version of Poisson summation that does hold for the indicative function, but unfortunately, it's a version for generalized functions. I say unfortunately because we didn't study it here, but I urge you to study it because it's a very useful theory. So it does include it. If you go to the land of generalized functions, sometimes called distributions, you can indeed have a Poisson summation for such functions like the indicative function. Since this is a rabbit hole of generalized functions that we'd rather not get into here, it's a very different kind of Alice in Wonderland. We'll simply say that this is an intuitive argument and we'll leave it at that for the moment, okay? It's also very instructive and useful to think in these terms of intuitive proofs, and then we can add vigor later as we learn more. So yeah, you can see our book also for a rigorous proof involving still functions, not generalized functions, once we convolve the indicative function with some other function. Okay, so that's it for today. Here are some exercises for you to grind your teeth on. Remember always to stay curious, always keep asking questions, keep asking yourself and us. And until next time, ciao.